This is Algebraic Methods Year 2, Chapter 1, and my videos are the only ones you need to understand the theoretical concepts. That's an absolute promise. And I'm going to start this video by looking at something which confuses a lot of people, and that's proof by contradiction. Proof by contradiction. That's a tricky one for some people. They really struggle to understand the essence of it. What's proof by contradiction trying to say? Now, before I explain it to you, I'll take a very simple example and you will start to get the essence. So I'm going to take an example. Proof by contradiction, P by PBC, I'm going to call it PBC, that there is no greatest natural number. How am I going to do that? Firstly, I'm going to say, suppose there is a natural number. I'm going to assume the opposite of it. I'm going to say, suppose there is a greatest natural number. Suppose, by the way, the natural numbers are from 1, 2, 3, 4, 5, 6 until you go on forever. But they start from 1. Suppose there is a greatest natural number, and I'm going to say we call it n. Or actually, let's call it k. Good. I don't know what that number is. Maybe it's 1,746,000,746. I don't know. Let's call it k. Then I'm going to say, consider k plus 1. It happens to be the case that if I add a natural number to a natural number, I still get a natural number. We have a plus 1 belongs to natural numbers, right? I can say that, good, because I just added a natural number. I added a 1 to a natural number, or by the closure property of natural numbers, k plus 1 is also a natural number. Fine. But k plus 1 is actually greater than k, right? K plus 1 is actually greater than k. So how did it happen that we assumed there was a greatest natural number, but we could find another one which is greater than k? So this has to mean that our assumption was false. This has to imply that there is the same statement, no greatest natural number, which I'm just going to bring down right here. There is no greatest natural number. So the essence is caught from something like this. We should actually know that a true statement, so the key essence here is that a true statement can never imply something false. A true statement can never imply something false. So what we said was, if this statement is actually true, if there is actually a greatest natural number, then I should not get a false implication. But I did get a false implication because I could find a number greater than k, which is also a natural number. So the only way that could have happened is this true statement wasn't actually true. It was false. But I wrongly assumed it was true. The essence is that a true statement can never imply something false. So this statement must have been false because it provided a false implication. If this statement was true, something like this would have never occurred. So if I take a false implication already, if I take 2 plus 3 and I call it 6 and say assume true, and then I add 1 to both sides, so I get 2 plus 3 plus 1 equals 6 plus 1 equals 7. But this is 6, right? 5 plus 1 is 6. But 6 is not equal to 7, is it? And therefore, this first thing could not have been true. It's not the greatest example because I assumed 2 plus 3 was 6. But you sort of get the essence. If I say 2 plus 3 is 6, I add 1 to both sides, I get 6 equals 7. But 6 is not equal to 7. So you get some idea. Let's look at a couple other examples. So I'm going to say, suppose P by PBC, proof by contradiction. Oops, I should not tell this. That there is no greatest odd integer, right? So I'm going to say, sure, let's assume there is one. Let's say there is a greatest odd integer. And we're going to call it, let's say this time, we're going to call it P. Now, since P is odd, we know odd numbers can be written in a specific format. So we know this implies P is of the form 2r plus 1, where r is a natural number, right? Well, if P is a negative odd number, well, let's just say where r is an integer. Good. Integers are negative, all the, let's say negative 10, negative 9, negative 8, all those negative whole numbers, and 0, and all the positive whole numbers. So nothing decimal or no fraction in integers, if you didn't know that. So P equals 2r plus 1. Where r is an integer. Now I'm going to say consider P plus 2. Consider, I'm going to call it S equals P plus 2 equals 2r plus 1 plus 2, which is 2r plus 3. Now again, 2r plus 3 is greater than 2r plus 1. But what is 2r plus 1? And 2r plus 1 is nothing but p. So I found that s is a number which is greater than p. It is also odd. And since I just added an integer, we know integers are closed under addition. So if I add something to an integer, I don't go beyond integers. So, and s belongs to integers. Therefore, we have a contradiction and there is no greatest odd number. So you're just going to fill it that this is a contradiction. There is no greatest odd number. You're going to fill it with that by this statement. You just bring that down. So again, we assumed something was true. Let's say there is a greatest odd integer. In reality, that's false. So it provides us a false implication. It's not a surprise that we got a false implication, because if this statement was true, we would have never gotten something like this absurd, that there is something which is a counterexample to that, right? If you start with 2 plus 2 equals 4, then you can never get 5 equals 7, right? If 2 plus 2 is 4, then 3 plus 3 is 6, 4 plus 4 is 8. You're never getting something absurd. If you got something absurd, that means the statement that you started with must have been wrong. Great. So these are two examples. Now we look at some tougher examples. So this is a very famous question. Prove by contradiction that root 2 is irrational. So you know the method by now. I'm going to say, suppose root 2 is rational, i.e. root 2 can be written as a fraction where top and bottom are integers and q is not equal to 0. And I'm also going to say this is in simplest form. Assume p and q are co-prime. Co-prime means they have no common factor amongst themselves except for 1. So this fraction cannot be simplified further. This is going to be a key statement. And every rational number can be written in that format, where the top and bottom are co-prime. Okay. So for example, I can say a number like 3 over 7, that's co-prime, right? So that's just one example. 3 and 7 are co-prime. Assume p and q are co-prime. Great. What I'm going to say is, let's square both sides. Okay. If I square both sides, I get 2 equals p squared over q squared, right? I just square both sides. This implies squared. 2q squared equals p squared means p squared is even. P squared is even, right? Because something is multiplied by 2 to get p squared, and multiples of 2 are always even. So p squared is even. But wait a second, only even squared is even. So that implies p is even. Because only an even number squared can produce an even number. 2 squared is 4. Oops. 2 squared is 4. 4 squared is 16. 8 squared is 64. Only an even squared is even. I should use small p. I keep changing the notation. P is even. Great. And now what I'm going to say is, if p is even, which is actually true by our assumption, then p equals to b for some b, right? Because an even number can be expressed as a multiple of 2. So p equals to b for some b. Good. And then I have 2q squared equals 2b whole squared, right? And this is from this equation. Now what I have is 2q squared equals 4b squared. But that means this implies 2q squared equals 4b squared. But this implies q equals 2b squared. Correct? Absolutely. But wait, this implies q squared is even. Q squared is even now because something is being multiplied by 2 to get q squared. And that by the same logic implies q is even. Okay, so do you see where this is going? We said p and q are co-prime and that we assumed root 2 is rational. But now we are getting something absurd. We are getting that both p is even and both q are even. So both p and q are even. But if they both are even, that means both of them are divisible by 2. So I can further simplify that fraction. But this should not have been possible. As I assumed p and q were co-prime, I assumed initially that this fraction is in simplest form. But now these two statements are telling me that they have a common factor of 2. So both p and q are divisible by 2. But this contradicts that p and q are co-prime. So root 2 is rational. Root 2 is irrational, which is our original statement of the question. Because we started with something absurd, that root 2 is rational, we got something absurd again, that p and q are not co-prime, even though we assumed they were co-prime. Every rational number can be written in a format where the top and bottom are co-prime. Hopefully you did understand that example. So here is the last example we are going to be looking at. All right, so you know how we are going to start this. I'm going to write the statement. So I'm going to say, suppose there is a greatest prime number or a largest prime number. If this is the case, if there is actually a largest prime number, then I can list all the prime numbers, right? Because I can make a list of them and I can say, yes, this is all the list of prime numbers. And the last element is the largest one. Then we can list all the primes. And that would be something like P1, P2, P3, and where all P's are primes. These are all prime numbers. So P1 might be 2, this is 5, until I get the largest one, which is something. Let's call it Pn, the largest, allegedly the largest. Now consider something. Now consider the multiplication of all these primes. Now consider P1 times P2 times P3 all the way up to Pn. Now, so I've multiplied all the primes together, and the number I get, let's call it Q, is quite an interesting one because it is multiplication of all the prime numbers, isn't it? Great. And I'm going to say, consider Q plus 1. Consider Q plus 1. Two things can happen. This is either prime or not, Q plus 1, because there are only two possibilities for a number. It can be prime or not. If Q plus 1 is prime, then we are done because Q plus 1 is larger than Pn, right? Because it was gotten by multiplying Pn by 2, 3, 5, 7. And so Q plus 1 is larger than Pn because these are all positive numbers. And yes, so then we are done. If Q plus 1 is prime, then we are done. We have shown that there is no largest prime. Then we are done because we already found something greater than the largest prime. But if Q plus 1 is not prime, then you ask the question, how can it be not prime? Because surely no prime in this list divides Q. Because if they divided Q, then the remainder would be 1. So let's say I take a prime like P3. I know P3 divides Q, so it can't divide Q plus 1, right? If Q plus 1 is not prime, then it must be divisible by some prime number in this list, right? Because every number has a prime factor. Every number can have a unique prime factorization. And if Q plus 1 is not prime, then it must have a prime factor in the list. But this is again a contradiction because no matter which prime I take and I try to divide Q plus 1, there will always be a remainder of 1. So this is a contradiction, as that would leave a remainder of 1. So I just bring the statement of the question. So there is no largest prime number, and we are done. That's your proof done. Perfect.